If you're watching this video series and you're just watching it for from a standpoint of net ionic equations and chemical reactions, then you're done. Now, if you're watching this from a standpoint of equilibrium and calculations and math, then hang on, there's a whole lot more coming. So what I've got here, I've got a comparison, and this goes right along with what we learned with our solubility rules, but now we're going to start telling the truth, okay? So we learned solubility rules, and those are like stereotypes. We're generalizing how soluble something is. And we say that sodium chloride is aqueous, but on the other hand, we say that silver chloride is a solid. Well, just how aqueous is it and just how solid is it? Those become questions that we encounter in equilibrium. So I pulled up a couple numbers here, and we're going to check these to see how true these hold as I go through the calculations. For sodium chloride, I found a value that says 357 milligrams per milliliter at 25 degrees Celsius. Now, you've probably at some point seen some solubility curves, and most substances, most ionic substances, some non-electrolytes as well, become more soluble as we increase temperature. Most of them do. There's a few that are exceptions to that, and you probably remember terms like saturated and unsaturated and supersaturated. Again, all of those going along with what we call solubility curves. Well, these things have solubility curves. If I check the milligram to milliliter ratio for sodium chloride, I should get something close to 357. On the other hand, for silver chloride, there is a small amount that's aqueous. Even though we call it a solid, we call it a solid because, notice this value, this is 1.9 milligrams, but it's not per milliliter, it's per 1,000 milliliters. So this is a really, really, really small amount. By comparison, this is a really, really, really large amount that we have for sodium chloride. So we're going to take those and we're going to do some conversions with those values. We're going to find just how soluble in comparison one is to the other. So I'm going to start with the NaCl, and for NaCl it tells me that I have 357 milligrams per milliliter. Now I want to put that in a gram to liter ratio, and we'll talk about why we do a gram to liter ratio once we do this series of conversions. So I'm going to convert my milligrams to grams. 1 gram is 1,000 milligrams. Milligrams cancel. And now to get rid of milliliters, it's on the bottom. I'm going to bring that to the top, milliliter to liter, and there's 1,000 milliliters per liter. Now, if you're looking at that from a standpoint of mathematics, you can go ahead and multiply across the top and divide by the bottom, but what we get is 357 grams per liter. That's called the gram solubility of sodium chloride. The gram solubility, how many grams per liter we can put into solution at 25 Celsius, and if we put 358, now all of a sudden that 1 gram is going to precipitate at the bottom. If we put 350, there's 7 more grams. At 350 grams in a liter, we have what's called an unsaturated solution. So 357 at 25 Celsius is the point of saturation for that. By comparison, for AgCl, we had 1.9 milligrams per liter. We're already in the proper units on the bottom. So now we're going to go milligrams to grams. 1 is 1,000. Milligrams cancel. And now we get 1.9 divided by 1,000, or 0.0019 grams per liter. So by comparison, we've got 357 grams per liter for sodium chloride. We've got 0.0019 grams per liter for silver chloride. So when you're learning solubility rules, you're generalizing how soluble these are, and we call this a precipitant, as long as we have at least 0.0019 grams per liter. As a matter of fact, for silver chloride, if I put 0.0007 grams in a liter container, it's not actually going to precipitate. It's too small to precipitate. So we'll talk about chemical reactions and what we do and why we flood certain values to try to drive precipitation. On the other hand, if we don't want it to precipitate, there's things that we can do, equilibrium, Le Chatelier's principle, to keep things from precipitating as well. And this is also, as I mentioned previously with the other one, this is called the gram solubility of AgCl. This is my gram solubility. Now from gram solubility, we're going to go into something called molar solubility as well. So I'll go back to my problem here with NaCl, and I'm going to find its molar solubility. And I can do that by simply converting 357 grams per liter. I want to go from grams to moles. So if I add up the molar mass of NaCl, I've got 23 and 35.45, so about 58.5 grams to the mole. And now I'm going to have a mole to liter ratio. Once I divide that out, 357 times 1 divided by 58.5, I end up with 6.10 moles per liter. Now, if you've seen that moles per liter before, you might be tempted to call this molarity, but when we're talking about the solid salt, we actually leave that as moles per liter. That's called the molar solubility of the salt, or of the solid. That's how many moles per liter we can get into solution. So it's not molarity yet. All right, we'll get to molarity here in a moment. Let's do that same thing with the AgCl that we have. We had 0.0019 grams per liter. From grams to moles for AgCl, 35.45 plus 107.9. And we end up with 143.35 grams per mole, 0.0019, divide by 143.35. And really small number that we're going to get here. This is equal to 0.000013, so I'm going to call this 1.3 times 10 to the -5th moles per liter. That's how many moles per liter of AgCl will go into solution. Alright, so now we're going to talk about these things actually going into solution, the next step of what we're going to do here. So we've got NaCl, and there's that dreaded equilibrium, and we're talking about the solid here. How much of it simply goes into solution. So we're just talking about the solution process. I am going to go into how we go from molar solubility, which is 6.10 for the solid, but I want to know what the concentrations of ions are. Well, this is actually pretty easy because it's 1 and it's 1. Now I'll show you some here in a little while when we get further into equilibrium where we don't have 1s. But what we get is a concentration of sodium ion of 6.10, but watch what happens here. Molar, because we're talking about how much makes a solution, what the concentration of the solution is. So again, trying to explain this term, the molar solubility of solid NaCl is 6.10 moles per liter. The concentration of the sodium ion is 6.10 molar. The concentration of the chloride ion is 6.10 molar. And now I can write what we call a equilibrium expression, or a solubility product equilibrium expression, KSP, and it's equal to products to their respective powers. Now, if you've just completed acid base, we've had a whole lot of 1s, and I've got 1s here, but we're going to see coefficients other than 1s soon enough. We've got Na concentration, Na ion concentration to the first, times Cl minus to the first, but the good news is, we put it over reactants, but notice what kind of reactant we're talking about here. We're talking about a solid, so we only plug in concentrations of ions. So in the case of KSP, we're only going to be talking about those product concentrations, 6.10 to the first times 6.10 to the first. So my KSP value for NaCl is 37.21, and I believe 37.2. I think we were 3 significant digits in that problem. 37.2 is my KSP, and that tells me that this lies heavily to the right, that this favors going into solution. So again, we learn those solubility rules because we're learning about KSP. We're stereotyping KSP without the numbers. Now we get into this, and it's time to plug the numbers in with it. On the other hand, let's see what happens when we do this with AgCl. Really similar equilibrium expression. Solid AgCl at equilibrium with Ag plus ions and Cl minus ions, aqueous. And my AgCl molar solubility was 1.3 times 10 to the negative 5th moles per liter. Again, that's the molar solubility of the solid. And since it makes 1 and 1, my concentration of Ag ion is 1.3 times 10 to the negative 5th. And my concentration of Cl minus is 1.3 times 10 to the negative 5th. And my KSP expression is Ag plus ions to the first times Cl minus ions to the first, and over nothing because this is a solid. So this is going to give me the KSP value for this. And I get 1.7 times 10 to the negative 10th. 1.7 times 10 to the negative 10th. Now that's a really, really small number, so that tells me that equilibrium lies heavily to the left, to the precipitant side, to the solid side. So again, that's why we learn the solubility rules early in chemistry, and now it's time to plug in some numbers and put with those. And the good news is, we're going to look at, how we go backward through this process. I took you from milligram to milliliter and milligram per liter to what we call gram solubility of the salt, to molar solubility of the salt, to molarity of ions, ultimately to something that we call KSP. But could we go backward? What if we had a KSP value and we wanted to do this process in reverse?